Hello, my name is Zmigrod, and I will be talking about work with Tim Vieira and Ryan Cotterell about inference using expectations in non-projective graph-based dependency parsing. First, a quick overview of graph-based dependency parsing. Dependency parsing is a task of predicting syntactic structure for a sentence, and graph-based dependency parsing works by converting a sentence into a dense graph where nodes are words and edges are possible dependency relations. We also add a root node to the sentence to mark the root of the dependency tree. We then compute scores for all edges in the form of an adjacency matrix using a learned model such as a neural network. In order to train a model, we need to minimize an objective function, often called a loss function. This is often the negative log likelihood of the target tree, but can be other quantities such as risk, entropy, or others. We decompose the weight of a tree multiplicatively over its edges, and so we can define a probability distribution by normalizing the weight of the tree by the normalization constant z. Although z is an exponentially large sum, we can use the matrix tree theorem to efficiently compute it in cubic time. The matrix tree theorem is just a matrix determinant of the Laplacian matrix, which is a simple linear transformation of the adjacency matrix. It is therefore very fast to compute and easy to implement through a linear algebra library. We are interested in computing expectations such as risk or entropy as our loss function. These functions take the generic form of the sum over all trees, where we take the product of the probability of the tree and some function applied to the tree. Note that this function does not have to be scalar valued. Using expectations in the loss function is useful for semi-supervised learning, where we can aim to minimize general properties of the data rather than pushing towards target values. Computing a generic expectation is intractable. However, we will examine a specific family of functions which we can leverage the matrix tree theorem for efficient computation. The family of functions we will examine are additively decomposable functions. A first-order additively decomposable function of a tree is decomposed additively among the edges. For a function r, we say that capital R is the dimensionality of the function, and r prime is the sparsity of the function. By sparsity, we mean the largest number of non-zero values in any given call to the function r. An example of a first-order expectation is the Shannon entropy, which additively decomposes into the negative log likelihood of the tree. Other first-order expectations are the KL divergence, risk, or the generalized expectation criteria. Additionally, the gradient of log z, which appears in the gradient of the log likelihood, is perhaps the most common example. We also examine second-order additively decomposable functions. These are functions that can be expressed as an outer product of two first-order functions. The gradient of any first-order expectation is a second-order expectation, and so we need it to be able to compute it efficiently. Similarly, the covariance matrix or the Fisher information matrix are examples of second-order expectations. Now, why do we care about these expectations? These expectations are very useful when training parsers and have been widely used throughout the literature. However, these expectations have been computed suboptimally in the past, and we hope to give a unified framework such that these mistakes are not made in the future. So what's our trick for computing these expectations efficiently? We rely on the fundamental connection between gradients and expectations, and can use concepts from automatic differentiation to know that we can derive efficient algorithms. Primarily, the cheap gradient principle tells us that we can backpropagate through a scalar value in the same asymptotic runtime as computing that value. We'll be working with totals, which are essentially unnormalized expectations. We will also define the total weight of an edge from I to j to be the sum of the weights of all trees that contain edge from I to j. This turns out to be equivalent to the derivative of z with respect to the weight of the edge, multiplied by that weight of the edge. We also have totals for pairs of edges that follow a similar pattern. First-order totals are then given by the following sum, and second-order totals are given by this sum. The proofs of correctness for these equations can be found in our paper. In order to have efficient algorithms, we need to be able to evaluate the derivative and second order derivative of z efficiently. We compute z by first building the Laplacian matrix and then taking its determinant. Therefore, its derivative requires a matrix inverse and applications of the chain rule. Finding the matrix inverse takes cubic time. However, as we will see later, we will only ever need to do this once. Fortunately, the derivative of the Laplacian is sparse, and so we can apply the chain rule very efficiently and derive the following equations for the first and second order derivatives of z. We can then compute a first order expectation by using the following three equations. We have to do an initial O of n cubed of work in order to get z and the matrix inverse of the Laplacian. Once we have those, we can do the sum over all the edges, which requires O n squared work. As each summand can reuse the same matrix inverse, we can find each summand in O of r prime time. This leads to a total runtime of big O of n cubed plus n squared times r prime. For entropy, we have that both r and r prime are equal to 1, and so the entropy can be computed in cubic time. We derive an algorithm for a second order expectation in a similar way. We again do cubic time work in order to get z and the matrix inverse of the Laplacian, and this time we have two loops. The first is again over all edges and takes big O of n squared times r prime times s prime time. The second is over pairs of edges, and so takes big O of n to the 4 times r prime times s prime time. This second loop dominates the runtime, leading to an overall complexity of big O of n to the 4 times r prime times s prime. However, we can use distributivity to get a faster algorithm. We will not go over the details of this, but by expanding all of the equations together, we can split the computation up into several sub-processes. This leads to a much faster algorithm that runs in the following runtime. Note that in some cases, the quartic runtime of the original approach is optimal, and this algorithm recovers that runtime. But in other cases, such as in the gradient of entropy, we have that r is 1 and s is n squared, but s prime is only 1, and so we can recover an even faster runtime of O of n to the 3. In this talk, we presented a unified framework for efficiently computing first and second order expectations for non-projective, graph-based dependency parsing models. We showed that we can compute many of these first order quantities in the same runtime that we compute the normalization constant. We additionally have a pretty efficient second order algorithm that lets us compute certain second order quantities in cubic time as well. Due to matrix operations of these algorithms, we are able to implement these with just a few lines of PyTorch. Thank you very much for listening, and our paper and code can be found using the following QR codes or links.